Alright, so this is going to be our second problem in trying to write equations for slope and displacement in a beam. Right now, the only tool we have is direct integration. And we've talked briefly that direct integration works really well on continuous loads. And you might see that this load is that. It's nice and continuous. So let's assume that that will work. So the next thing we have to decide, or the next thing we have to perform, is I need the moment equation for this structure. So to help you visualize that, I'll just make an arbitrary cut somewhere in the structure. And then we'll decide whether we will work the free body diagram on the left-hand side or the free body diagram on the right-hand side. And we've probably done enough of these that in this particular case, you'll probably think the left-hand side is going to be the easier of the two. And I will agree with you. So we'll go left-hand side. And I'll also modify this slightly to say this is going to be at some distance x. Now, once I've made that decision, you can see I need to know what's happening here at A. It's a pin, so there's no moment, but there will be a reaction. AY. Now, I'm not going to worry about AX because axial forces won't affect our moment anyway. Now, there will be a time in the near future where we will be concerned about the axial force because we'll also want to include that in our calculation for displacement. But for right now, I won't worry about it. So I just have this one unknown. So looking at the whole structure as a free body diagram, how do I find my reaction at A? You probably want to sum moments at B. So I'll do that. So I'll come over here and say, using right-hand rule for my sign convention, I will sum moments at B and make sure it's in equilibrium. So that's what I want to do for equilibrium. And what do I have? Well, I'm going to need to do something with this distributed load. So the easiest thing to do is to get a concentrated load that's equivalent. And we know for a rectangular section that the area of a rectangle is base, in this case L, times height, W. So this force becomes WL. And where's the centroid of a rectangle? Right in the middle. So that would split our L in two, so we'd have a distance of L over 2 on either side. So summing moments about B, then you can see our concentrated equivalent force creates what kind of moment about B? Positive or negative with right-hand rule? Positive, right? So the force would be WL, and the distance would be L over 2. And the other force in the system is AY, and that creates negative moment. And it has a force of AY. And its distance is the distance between A and B, which is L. So you can see that the reaction at A is going to be WL over 2. And that's not surprising. You probably expected that. You'd expect that take the total load. In this case, half would be to A, half would be to B. And that's what we got. We got half of it. So now I'm going to go back and draw the free body diagram that I just mentioned before in a little more detail. So here's that section of the beam. We just found that our force here at AY was WL over 2. Right? And then we have this portion of the load. That had an intensity of W. This has a length of X. And then all we're really concerned about right now is the moment. So I'll draw my positive bending moment there at the cut. So just like we resolved the distributed load up here to make it easier, we're going to do the same thing here. So I'm going to have a concentrated equivalent force. Now that force is going to be this area. It's a rectangle still, as before. But now the rectangle is going to have a base of X and a height of W. So that will be WX. And the centroid will be located at half the distance. The distance is x, so that distance away will be x over 2. So now when I sum moments at the cut and put an equilibrium, let's see what I've got. So here at the cut, I've got this moment, which for my sign convention, that's positive. About the cut, the Wx force creates what kind of moment? Positive. So I have a force of Wx times a moment arm of x over 2. And then my reaction here at A, that creates what kind of moment? Positive or negative? Negative. And that will be a force of WL over 2, and it'll have a moment arm of x. So far, so good? So we'll just solve for the moment. So the moment as a function of x is going to be equal to what? I'm going to get Wx squared over 2, that's going to be negative, plus WLx over 2. Here's my moment equation. Now I could tidy this up a little bit. You can see all the terms have a W in the numerator and a 2 in the denominator, so I can eventually factor that out. Now remember, our next step is to do what? We're going to try to calculate the slope, and we know the slope is the integral of the moment divided by EI. So in this problem, E and I are going to be constant. And you also see I've got a W over 2 that's constant. So I'm going to factor all that out. So I'm going to end up with W over 2EI. And then I'm going to have the integral of what's left over, which would be minus x squared plus Lx dx. Did I do that right? So far, so good? You can see that's a pretty easy integral to do. So my constant still stays there, W over 2EI. And then what do I get? This becomes minus x cubed over 3 plus Lx squared over 2. And then plus my first integration constant, C1. Did I do that right? You guys following along? It's hard to know. You're a quiet bunch. Now, just looking at this, our boundary conditions of pin and roller tell us that I know the displacement is 0 here, and I know the displacement is 0 here. But I don't know the slope here or the slope there. So for right now, I'm just going to leave my slope equation alone. I don't really know much about slope. Now there is one condition that I do know, but I don't want to talk about that one right now. So like right now, I've just got, hey, I know the displacement here is 0. I know the displacement here is 0. I don't have a slope equation. I don't have a displacement equation yet. So let's do that. I know displacement is the integral of slope. So let's integrate this equation one more time. What do we get? Well, that W over 2EI is still a constant. So the integral of this becomes minus x to the 4th over 12 plus Lx cubed over 6. C1's a constant. I integrate that, I get C1x. And then, of course, I generate another integration constant, C2. So now I got an equation for displacement and two conditions, two constants. But I got two things to match it to, right? Here and here. Yes. So my two conditions are, I know that at y, at x equals 0, it should be 0. And I know that at y at x equal L, it also should be 0. Which one of those is going to be easier to do first? Well, x equals 0 is probably pretty easy to do. So let's do that one first. So at x equal 0, plug in 0 here, what do you get? 0, 0, 0. All you get is C2. So that means C2 has to be 0. So far, so good. Got one more to do. What about when x is equal to L? Well, I know that's also 0. So let's plug in x equal to L here. All right, so I got L to the 4th over 12 plus L to the 4th over 6. Okay. So this is a 12th and this is a 6. So that a 6 is really 2 12ths, right? So I got 2 12ths minus a 12th gives me just a 12th. And I multiply by all that, and what do I get? I get WL to the 4th over 24 EI. So all of that turns into that. All right? And then I got plus C1 times L. And we already know C2 is 0. So can you solve for C1? Remember, this whole expression has to be equal to 0. So what is C1? It's negative WL cubed over 24 EI. All I have to do is plug these values for C1 and C2 back in either of my expressions and have an equation for slope and equation for displacement. Let's do the displacement one first. So the displacement at x is going to be what? What's all this stuff? W over 2EI minus x to the 4th over 12 plus LX cubed over 6. That's what we found before. Plus C1 times x. Well, there's C1. So it's minus WL cubed x over 24 EI. An ugly equation. And I bet if you looked at it long enough, you would see that they've all got W. You could probably do something with this L and X. This E and I is in the bottom. 2 times 12 is 24. There's a 24 there. You can probably collect a bunch of terms if you want to. There's no advantage to that. If you're doing this at home or you're doing this in the test, that's good enough for me. You don't have to spend some time simplifying and expanding and all that. But we do need to check it. Does it still work? Well, when x is equal to 0, what happens? 0, 0, 0. So that one still works, right? What about when x is equal to L? Well, we've done this before. When I plug x equal L here, I get positive W L to the 4th over 24 EI, and I plug in x equal here, I get negative. So it works there too. So everything works. So that's a valid equation for displacement. So where's the displacement maximum? Now this one's kind of easy because it's a simple supported beam, uniform load. Maximum displacement is going to be right in the middle. In general, you wouldn't know that. So how would you find where the displacement was maximum? Well, we know where something's maximum, its derivative is probably 0. And what's the derivative of displacement? The slope equation. So I'd go back up here to my slope equation and set it equal to 0 and find what values of x gave me that. The only problem here is if you look at our slope equation, what is it? It's cubic. off the top of my head, I don't know how to find the roots to a cubic equation. I know the quadratic equation, but I don't know the cubic equation. That's a little tricky. At home, you would have resources, and you could probably do that. So when you solve for these three roots, what do you expect to get? Well, you should get one that's between 1, 0, and L. That's the only one that's real. You may get one that's greater than L, which doesn't make any physical sense. You might even get one that's negative L, which doesn't make any physical sense either. So there's only going to be one root, even for however many you generate. There's only going to be one root in your system, probably, for our simple problems. That makes sense. The other ones won't make any sense. But if you wanted to, just for fun, I know you guys are having lots of fun with this. Let's look at the value when x is equal to L over 2, which is right in the middle. This is going to take a little time because it's L over 2. So you put L over 2 in here and you raise it to the 4th power, what do you get? Well, you get L to the 4th, and then what's 2, 4, 8, 16, and then what's 16 times 12? 256? I don't know. 300 something?
192.
192? And then times 2?
384.
384. So this is going to be 1 384th. And this is going to be what? I don't know. Let me write it here. This is going to be 1 384th. Now this is only cubed, right? So that's going to be L to the 4th over 8. What's 8 times 6?
48.
48 times 2. 96? So 96 goes into there how many times? 4? So this will be 4 384ths. And of course this one's negative. So you can see now we got 3 384ths there. What about this guy? That's just L straight up. So there's L to the 4th, and that's 2, right? Times that is 48. You guys with me so far? No, I lost you? So what's, how many times does 48 go in here? I would say 8 times. So this becomes then minus 8 384ths. So you add all that up, and what do you get? Minus 5 384ths. So I think this is going to be negative 5 WL to the 4th over 384 EI. I think. Does that seem reasonable? You have no idea. You guys don't like this at all, do you? Well, if you look at the front of your book, there's the problem. Oh, they go the other way. And what's the maximum displacement? There it is. That's the same thing we just got, right? See, it works. And you'll notice that they made their equation a little prettier than ours. And you notice they're using a terrible notation, capital V for displacement. When we use capital V for shear, I don't know what this guy was thinking. I think we got some problems there. In previous editions, he used a lowercase v, kind of a squirrely scripted one. And I've also seen it just written with Y. So you just have to get used to the fact that everybody kind of uses whatever notation they like. Oh, that's really big. Sorry about that. You're probably getting seasick now thinking you're on top of a 100-story building. All right. So for me, this would be enough right here. This is the solution to the problem. All right.